afternoon to all IEM and UEM family members. Hope you are all doing well. I'm feeling really honored to speak in front of you after a long time, although I won't be speaking today, but I'll be introducing our professor, Anamika Khaskel. She is Associate Professor of BSH Department of UEM Jaipur. She will be talking on various aspects of multi-component reactions in synthetic organic chemistry. So definitely it will be a very enjoyable session. Hope you will all enjoy this session. We will have 2 polls in between this lecture, as you all know. So over to Professor Anamika Khaskel. You, ma'am.
Thank you, ma'am. Good afternoon to all. I think I'm audible and visible also. So today I discuss about the one topic. The name is various aspects of multi-component condensation reaction. So I'm starting my presentation right now. So first of all, the topic is various aspects of multi-component condensation reaction in synthetic organic chemistry. In this topic, first of all, I discuss about what is synthetic organic chemistry. What is the main role of the synthetic organic chemist? Synthetic organic chemists have the power to replicate some of the most intriguing and important molecules of living nature in the laboratory and apply their developed synthetic strategies and technologies to construct variations of them. This is the main pillar of the synthetic organic chemist, and how synthetic organic chemists are related with their multi-component condensation reaction approach. Right now I describe about this. Before I discuss this, today my presentation, I divided my presentation in the following content. First is introduction. Second is examples of MCR. Third one is history of MCR. Fourth one is pedagogical importance of MCR. Next is importance of MCR in the organic synthesis. And last one is the conclusion part. So I just come to this part. Actually, I think there is a problem. Screen is, hello?
Yes, any problem?
Ma'am, PPT is not moving actually. This is the main problem.
You do one thing, you first shut down once again. You don't have to shut down, just go out of this PowerPoint software and again you restart it once again. Yeah.
I think it's okay.
But you are not visible.
So, it is visible now?
Yes, the screen is visible, but you are not visible.
Okay, okay. So this is the introduction.
You make your webcam
no,
on.
Webcam. I off the webcam because internet problem is also there. So that is why I'm just off the webcam.
Okay. Okay.
So for the intro, we divided our presentation in the following contents. Say, first of all, introduction, examples of MCR, history of MCR, pedagogical importance of MCR, importance of MCR in organic synthesis, and conclusion. Before I discussing the introduction part, I come to the important portion. What is MCR? That means what is multi-component condensation reaction is. Multi-component condensation reaction, or MCRs, sometimes referred to as another name. It is called the multi-component assembly process, or MCAP. It is a chemical reaction where 3 or more components come in contact in a single pot and generate a new product. As for example, if you take this is the aldehyde RCHO. When it combined with the carboxylic acid, say RCOOH, and isocyanide, this is a 3-component reaction. That is 1, 2, 3 components are related with, and after they are combined with each other, they generate a new adduct. The name of this adduct is called the Pasirini adduct, and the compound name is alpha acyloxyamides. Now, another important part is that carboxylic acids, aldehyde, and isocyanide in presence of amine combine with each other and they generate another product. This product is called the UGI adducts. So this is the 4-component condensation reaction. Right now, I just give the multi-component condensation reaction and stepwise component reaction according to their pictorial viewpoint. Say, let us take the example. This is the multi-component condensation reaction. The product is formed in this multi-component condensation reaction, and in the stepwise condensation reaction, both the cases, products are same. But if we use the multi-component condensation approach, you get that, say this is the reactant. So red circle, blue triangle, green square, when combined with each other, they generate a single entity. This is the product we get, but we can generate this entity just in a 1-step procedure. But if I consider this pathway in the stepwise manner, we get that this red circle combined with the blue triangle, it generates the red and blue entity, then it will generate the green entity, and it will give the red, blue, and green, the same product, by the 2-step process. So we understand that multi-component condensation reaction or 1-pot condensation reaction or single-step condensation reaction definitely beneficial than that of the stepwise reaction, because it will be much more cost effective, it will be much more labor saving, it will be much more eco-friendly. Because if we consider 2 or 3 steps, in all steps individually we are using small portion of the solvent, and volatile solvent are very toxic for our environment also. So in the 1-step methodology, we can use just only small amount of solvent in a single step, so we can achieve the particular compound. So this is the pictorial representation of stepwise and multi-component reaction. Now I describe that what is multi-component condensation reaction. In German word, it is called the Kinderle or Kinderlight. This is called, that means child's play or deadly easy. It is called the child's play or deadly easy. So I can take the example, that is if this is the entity, we want to synthesize this compound. We can synthesize this compound using the number of steps, or you can synthesize this particular compound just a single step. So if we want to synthesize this compound and we consider the stepwise reaction mechanism, that is this blue component will attach with this green component, it will give the blue-green entity. Then this blue and green entity will attach with the red component and it will give the blue, green and red entity. And at last, this blue, green and red entity will combine with the orange entity and it will give the blue, green, red and orange. This is the final product. But we have to here, if we consider for the stepwise reaction, we have to follow at least 3 steps here, 1, 2, 3. But if I consider we want to synthesize the same product using the multi-component condensation reaction approach. This is nothing but the example of the children are assembling the blocks. If the 4 children are present here, they individually have the one block, colorful block. They are just assembling this block, and after assembling this block, they synthesize this particular compound. So this is the beauty of the multi-component condensation reaction, and that is why in this particular journal, American Chemical Society Journal of Chemical Education, they told that this is nothing but the child's play or deadly easy. Next, I come to the part MCR versus multi-step reactions. So for MCR versus multi-step reaction, the multi-component condensation reaction, say I just give the example that 1, 2, 3, the 3 components when combined with each other, they generate a particular product. This is an example of the 3-CR reaction, because this involves the 3 components are attaching with each other. If 4 components, say 1, 2, 3, 4, are reacting with each other and they generate the 4-component reaction approach, 4-component molecule. So it is the example of 4-component reaction. Now another example, say 1, 2, 3, 4, 5, and 6. These 6 components, if combined with each other and they generate a new product, this is also an example of the 6-component condensation reaction. Now we can take the example that if a single reaction flask, say in any single reaction flask, we just attached, added the components, say P plus Q plus R. When they react with each other in a single pot, they generate the product. This is the PQR. So this product definitely has this reaction methodology has the higher efficiency because it is the single step reaction. It has higher diversity per step. But if I consider the same reaction is going on in the multiple step, say in a single reaction flask, we attach A, then attach B. Then AB is formed. Then the next step, we attach the C and we get the product ABC. So in respect of efficiency and diversity, definitely the stepwise reaction will be have the low efficiency and low diversity per step. Next, we can compare the MCR ideology, that is multi-component condensation reaction ideology, with a combing lock joint. That means diagram of motifs and tenon joint. This is the motifs and this is the tenon. When they're combined with each other, that means this is called the combing lock joint. So MCR is like that. That means 3 entities, that is 1, 2, 3, combine with each other and they join the assembly to combing lock. Now we describe some significance of multi-component condensation reaction. In multi-component condensation reaction, swift assembly of huge molecular diversity is a most important area for synthetic organic chemists to synthesize this type of compound, and it is the key patterns of modern drug discovery. It involves the combination of 3 or more multiple reactants together in a single reaction flask or single reaction pot to generate a product incorporating most of the atoms contained in the starting materials. It develops new chemical entities with a desirable properties in a more efficient, time-saving, more economical and cost-effective way. So we describe the few advantages of the multi-component condensation reaction. First of all, convergence, high yields, parallel approach, sustainability. This is the very important part from the multi-component condensation reaction. Easiness of performance. Easiness of performance means we can synthesize the many pharmacologically active compounds in the laboratory using the multi-component condensation approach very simple way. That is why we can enlist the multi-component condensation reaction synthesis in an undergraduate course also. We can discuss it later. In our later slide, we'll discuss this part. Very large chemical space, very large scaffold space, complexity generation, diversity generation. These are the main aspects of multi-component condensation reaction. Now I describe the advantages of multi-component condensation reaction. What are the main advantages of MCR? It can start with the readily available starting material. Next is, it is very simple. That is because it is the one-pot condensation, so it is very simple. Most of the time, the reaction gives very high yield. It gives the total conversion. Environmentally friendly because this is the single pot reaction, so we can easily apply the less solvent use. So different type of solvent we can use, that is we'll discuss later slide. So that is why this procedure is environmentally friendly. This is the one pot procedure. This is resource effective and it is very safe methodology. So these are the main advantages of multi-component condensation reaction over linear synthesis. Next, I come to the part, what is heterocycles? Because heterocycles are the most important components, because if we synthesize the heterocycles in a very easiest way, that means if we synthesize the heterocycles using the approach of the multi-component condensation reaction technique, this will be very beneficial for the organic synthesis. And most of the multi-component reactions are used to synthesize the different types of heterocycles. Ring compounds with elements other than carbon in the ring, the most common elements to appear in heterocyclic compounds are oxygen, nitrogen, and sulfur. Let us take the example. Say this compound, this is a ring compound, but it has some heteroatom. This is the nitrogen and nitrogen. So this ring compound is called the imidazole. Now this compound, this is the heterocyclic ring is present and one heteroatom is present. So this compound is called, has the sulfur heteroatom. Next we come to the part 6-membered heterocyclic ring. This is the compound is called the pyridine. Next compound is called the imidazole, imidole, and last one is called the oxazole. Now heterocycles in our body. Heterocycles are the essential elements in our body. So let us take the example, nucleobases of RNA. That is cytosine, guanine, adenine, uracil. These nucleobases of RNA, these all are the heterocyclic compounds. Same thing, nucleobases of DNA, we observe that cytosine, guanine, adenine, thymine, these also are the heterocyclic compounds. So synthesis of the different types of heterocyclic compounds is a very important phenomena if we use the multi-component condensation reaction approach. Now I just describe the few names of the important MCR reaction. Say Hans synthesis, Giward reaction, Staker reaction, Ugi reaction, Manic reaction, Bucherer-Bird's reaction, Biginelli reaction, and Pasirini reaction. I'm not discussing all the name reactions, name multi-component condensation reaction. I just take few examples. And first of all, I brief the history of MCR. First MCR was reported by Staker in 1850. Then come the Hans reaction approach. In the Hans reaction, it will come 1882, it came, and Hans synthesized different types of 1,4-dihydropyridines. Next come in 1891, Biginelli synthesized different types of dihydropyrimidinones. Next come the Manic reaction approach, and he synthesized in Manic compounds in 1912. Next come to the Pasirini reaction. It came in 1921. And using the Pasirini reaction concept, alpha acyloxy amide is synthesized. And last one is 1959. This is the very important reaction, name is Ugi reaction. And through this Ugi reaction, biamide are easily synthesized. And this Ugi reaction is the pathway, it opening the new pathway for the combinatorial chemistry also. So the main behind the MCR, these are the important persons who are responsible to make MCR very easier for the organic synthesis. So first of all, this is Pietro Biginelli. Next, A.R. Hans. This one, M. Pasirini. And last one is I.K. Pugi. Right now, I describe the individual
Sir, Anamika Khaskel, you are not audible right at this moment.
five molecules of HCN in a multi-component in a MCR catalyzed by ammonia. So from the toxic elements, we generate the very important essential elements in our body part. So this is the beauty of the prebiotic synthesis of adenine. Next, we come to the part first multi-component reaction, and the first multi-component reaction reported by Staker in 1850 for alpha amino acid synthesis. So Staker reaction is the first alpha amino acid synthesis for the first multi-component condensation reaction, where we observe that aldehyde, ammonia and HCN and H plus H2O combine with each other and they generate the amino acid, alpha amino acid. Next, we come to the part in 1891, Pietro Biginelli reported a very useful multi-component reaction for the synthesis of pyrimidinones. In this reaction, we observed that aldehyde 1,3-diketone or beta-ketoester and urea or thiourea combine with each other in a single pot and they generate the dihydropyrimidinones. So NH C double bond S or NH C double bond O NR or NH. So this is called the Biginelli reaction. Now, what is the significance of the DHPMs? DHPMs has huge significance in their medicinal impact. First of all, it has the antiviral activity, anti-tumor activity, anti-inflammatory activity, antibacterial activity, and anti-cancer activity. Next slide, we describe the monastrol, a promising anti-cancer agent. Monastrol is a very promising anti-cancer agent. It is substituted by the 3-hydroxybenzaldehyde. It is also, there is one moiety is there from thiourea and another part is ethyl acetoacetate. So we can consider that monastrol synthesis is possible in the very easily. We can synthesize monastrol using laboratory by the concept of Biginelli reaction. When you combine the thiourea, ethyl acetoacetate, and 3-hydroxybenzaldehyde in a one-pot reaction vessel, we can generate the monastrol very easily. Now, another important part is seleno-DHPMs. Seleno-DHPMs, a potential multi-targeted therapeutic for Alzheimer's disease. You know this is the DHPM's moiety, that is NHCONR. This is the DHPM moiety is there and this is the DHPM code is there. Now, interesting thing is that Alzheimer's disease, for the medicine of the Alzheimer's disease, if DHPM is incorporated with the selenium, organoselenium moiety, it will be very beneficial for the multi-targeted therapeutic for Alzheimer's derivatives. So let us take the example. We can synthesize the DHPM core organoselenium moiety very easily by the help of Biginelli reaction. So first of all, we have to use this is the part will come from the aldehyde section. So this aldehyde, we are using the aromatic aldehyde. using the urea, but here NR is there, that is substituted urea is there, so we are using RNH2. And last one, we use that. Actually, first case we use the ethyl acetoacetate, but here we using ClCH2CO, CH2COOET, because we have to incorporate further the selenium moiety. That is why we are using the CH2Cl part. Now what happens? When they combine in presence of HCl, they generate the DHPM compound, dihydropyrimidinones. Now this DHPMs, when react with the KACCN, this KACCN, that is potassium selenocyanide, this Cl will be removed, and after the removal of the Cl, we get there is a formation of the ACCN, selenium cyanide. So selenium already incorporated here. So by the use of Biginelli reaction, we can easily synthesize organoselenium moiety. Another approach we can use, I am not showing this is in the PPT. So if I, instead of using this compound, if we use the simple ethyl acetoacetate, aldehyde and selenourea and just take the reaction in presence of HCl or any other catalyst, so we get the incorporation of the selenium group in place of oxygen. So this is also very much important, a potential multi-targeted therapeutic for Alzheimer's disease also. Right now, extension of the Biginelli reaction, here we describe, that means synthesis of 1,3-diketone or methyl or ethyl acetoacetate in presence of aldehyde in urea. It is very easier way to synthesize the Biginelli DHPMs. But instead of using the 1,3-diketone, if we use beta-oxodithioester, this is the beta-oxodithioester in presence of aldehyde and particular catalyst and urea, we can generate this new moiety C double bond S SME. So this moiety is the gateway for the synthesis of many other pharmacologically important drug also. So that is why we can consider that just changing the different substituent, we can change the different DHPM compounds. So this is the main importance of the Biginelli reaction. Right now, I can give another example. This is the extension of the Biginelli reaction. We describe only the Biginelli reaction for 1,3-diketone or diketoester only. But we can use the ketone. If we use the ketone, aldehyde and thiourea in presence of HCl and ETOH, we can also synthesize DHPM compound. So instead of using 1,3-diketone or ketoester, we can use ketone also. Another important thing is that it is observed that if the Biginelli reaction is performed using the ferrosinyl substituent compound, that is ferrosinyl aldehyde or anything else, this compound is pharmacologically very important. So this is the just discussion about the probable reaction mechanism for Biginelli reaction. Biginelli reaction undergo the following mechanism. Again, I am not elaborating this part because this is the go through the iminium route. Next one is the enamine route, and third one is the novenagal route. Though 3 routes are possible, but right now the actual mechanism is not clear about the Biginelli reaction. Now the next reaction is the Hans synthesis, and it was first discovered by Arthur Hans in 1881. That means the first reaction comes the Stecker multi-component condensation reaction, then come the Hans reaction. In this Hans reaction, we observe that 1,3-diketone or beta-ketoester, ammonia or ammonium acetate or aldehyde, when combined with each other, they generate the Hans 1,4-DHPs compounds. This is called Hans 1,4-dihydropyridines. This compound has the huge significance of 1,4-DHPs due to its calcium channel modulator, cardiovascular drugs approach, anti-cancer drug, anti-hypertensive drugs. So these are the market common high blood pressure drug, which is very much present in the market. This is called the Nepetine. So from the Nepetine, this moiety we can synthesize easily using the help of Hans 1,4-dihydropyridine. So let us take the example. If we choose 2-nitrobenzaldehyde and methyl acetoacetate 2 moles and ammonium acetate or ammonia in a single pot, we can easily generate the nepidapine. So these are the some biologically active 1,4-DHPs. This is the felodipine, nimodipine, and amlodipine. Next, I come to the part, the history of nepidapine. Nepidapine has a long history in medicinal chemistry. It was first synthesized in the mid-1960s. Then the Bayer Pharmaceutical Company, who invented this for the vascular smooth muscle. But next, due to the impressive pharmaceutical results as its calcium channel blocker and was patented, it was patented in 1971 and sold on the German market in 1975 with the commercial name Adalat and received an FDA approval in 1980. Since then, it entered the global market and went on to become the second most sold drug from Bayer in 1980s. Madam, I will request for the poll, first poll.
Yes, sure. I'm launching the first poll. So now I'll be showing the responses that I have obtained to this first poll. This is the result. First sticker 46%, beginnerly 39%, Hans's 14%, and UGI 1%. Professor Anamika?
So
yes.
Please tell me repeat the result again.
Yeah, Staker 46%, beginnerly 39%, Hans's 14%, and UGI 1%. This is the result of first poll.
Okay. So the sticker is 46%. It is the correct answer.
It is the correct answer. Okay.
Yes. Next I come to the slide. This is the UGI reaction. So UGI reaction. In this reaction, it is also, and the UGI reaction is a multi-component reaction. In organic chemistry involving a ketone or aldehyde, an amine, an isocyanide, and a carboxylic acid to form a base amide. This reaction is named after Ivar Karl UGI, who first reported this reaction in 1959. We observed that in this reaction, carboxylic acid, amine, ketone, isocyanide combine with each other, and this is the huge atom economy, and water will be removed from this section and it will generate the bis amide product. And this is the first published article written by UGI. I just attached the cutting of this public manuscript here. Next, I come to the part application of the UGI reaction. This drug is named Indinavir, and trade name of the drug is called the Crixivan. It is made by Merck, and it can be used to treat HIV or AIDS. It was patented in 1991 and approved for medicinal use in 1996. Indinavir does not cure HIV or AIDS, but it can extend the length of person's life for several years by showing the progression of the disease. So if we consider the UGI reaction, using the UGI reaction just only using very cost-effective manner, we can synthesize the pyxevan. Next, come to the Pasirini reaction. This Pasirini reaction is a very important reaction, and in this reaction, alpha acyloxyamide synthesis will take
Professor
place.
Anamika, Professor Anamika, I'm just interfering because your PPT is not visible right now. Because many of the professors right now, they are saying that they also cannot see. In fact, I am also
Okay,
unable
just
to.
I just take it. I just check. It is right now visible?
No, no, no.
Let us take this one. It is visible right now?
Yes, yes, it's not visible. Yes,
Okay.
it's not visible. I think all of you can.
Okay, so I think I will take this description also, that is called the UGI reaction. What I described, that this is the Indinavir. It is the trade name is pyxevan, but it is used for the HIV or AIDS, and using the Pasirini reaction approach, we can synthesize easily this reaction. Next, I come to the part. This is the Pasirini reaction. In the Pasirini reaction, we observed that alpha acyloxyamide synthesis. This reaction was also very important for the multi-component reaction respect. This was discovered by Mario Pasirini in 1921, and he is from Florence, Italy. It is the first isocyanide-based multi-component reaction. That means we can understand that UGI is also the isocyanide-based multi-component condensation reaction, but Pasirini is the first isocyanide-based MCR, and currently plays a central role in the combinatorial chemistry. So we observed that carboxylic acid, ketone, and alkyl isocyanide combine with each other and they generate a new component. This is called the alpha acyloxyamide synthesis. Now, these are not the very famous reaction, but right now it is very common for the synthesis of multi-component approach. This is the bis-indolyl methane synthesis, where 2 moles of indole combine with each other with an aldehyde, generate the bis-indolyl methane. If we change the different types of R dash, we can change the different derivatives also, and we can check their different types of biological property. Next, this is another example for the dicumaral synthesis. This is very important synthesis where 2 moles of 4-hydroxycoumarin react with the aldehyde and generate the bis 4-hydroxycoumarin compound. So this is one of the important MCR. Right now, I just give the available drugs possessing dicumaral scaffold. So these are the important drugs which contains the dicumaral scaffold. That means this drug we can achieve in the laboratory by using the bis 4-hydroxycoumarin multi-component condensation reaction approach. Next, we come to the very important part. This is called the, in Journal of Organic Chemistry Frontier, it is available, this report is available, that MCR and drug discovery, multi-component condensation reaction technology is now widely recognized for its impact on drug discovery projects, and is strongly endorsed by industry as well as academia. However, still relatively few products based on MCRs are marketed or under development. Example, Recent example of the HCV drug, that is, I can consider that telaprevir. This is the telaprevir, is highlighted here. This drug, when we have to synthesize the telaprevir in the stepwise manner or the linear synthesis, it requires lots of time. It is not so economical procedure. But when multi-component condensation reaction approach came, then using the two multi-component condensation reaction, that means Pasirini and UGI, the synthesis timing of the synthesis will be very low. Actually, it is called that recent example of the HCV drug telaprevir is highlighted, where the introduction of the two MCRs could lead to a shortening of the synthesis route by more than 50%. Now, I describe the pedagogical section, because in the content part, I describe that the importance of pedagogy in the multi-component condensation reaction, and we describe our work also. So first of all, efficiency in accessing the complex heterocyclic structure in one-step multi-component reaction, MCRs, have been widely adopted in organic research and industry. Following the same trend, the number of undergraduate organic laboratory experiments, because undergraduate students, if they get the proper training, how they perform the reaction in their near future, in their research work, etc. So it will be very beneficial for them. Using MCRs has also increased in recent years. So MCRs have the advantage of conserving most of the atoms from the building blocks that are present in the product to generate a libraries of compounds, and it will open the new window for the combinatorial chemistry also. So MCRs can be used to introduce the concept of combinatorial chemistry as a tool utilized in drug discovery to undergraduate laboratory curriculum. Now I describe our work. We reported one work and we enlist one course, design the laboratory experiment for the undergraduate level. We performed this experiment in the laboratory of NIT Silchar for the MSc students. So let us take the example, bis 4-hydroxycoumarin synthesis, a very simple reaction methodology by which we can consider that in this reaction, we use the bis 4-hydroxycoumarin. This bis 4-hydroxycoumarin, what we synthesize in our work, this work has been published in the Journal of Chemical Education, American Chemical Society. So we describe our work. That is 2 moles of 4-hydroxycoumarin, when combined with the aldehyde, they generate bis 4-hydroxycoumarin in presence of antimony and ethanol. Ethanol we use as solvent, triphenyl antimony we use the catalyst. Here, first of all, we get the approach that there is a Novenagal reaction methodology, then there is a formation of the Michael reaction approach, then there is a enolization, and we get the bis 4-hydroxycoumarin. In the experimental result, we received that we implemented this reaction for the 5 aldehydes. Say first of all, NME2CHO, parachlorobenzaldehyde, paramethoxybenzaldehyde, 3,4,5-trimethoxybenzaldehyde, and thiophene-3-haldehyde. When you synthesize this, we observed that each group was provided with one unknown aldehyde by the laboratory assistant. Each group received the list of plausible aldehydes, and the pedagogical goal is to synthesize the specific bis 4-hydroxycoumarin and identify the structure of the unknown compound from spectral data. This was our main goal. So students synthesize the compound, they perform the experiment in a particular group, and if there are 20 students are present, the groups are 4 groups are formed, and each group contains 5 students. So first of all, I just take one example. 4-methoxybenzaldehyde substituted bis 4-hydroxycoumarin and 3,4,5-trimethoxybenzaldehyde bis 4-hydroxycoumarin they have synthesized. And when they take the 13C NMR spectra, they observe that this OME group has the 54.96 13C NMR spectral value. This has the 60.10 and 56.07 value. So they can differentiate these two compounds, though they have the same melting point. So this is our pedagogical goal of this particular reaction. And if we search this reaction, you can get this in this particular journal, this result. Next, I come to the part, the pedagogical outcomes of the experiment, what we develop for the undergraduate course. First one, achieve a deeper understanding about MCR. B, understand the characterization of the unknown products through the melting point, NMR, and FTIS spectroscopy, also HNMS spectra. Understand the concept of depth NMR spectra. Demonstrate the knowledge of monitoring the completion of the reaction by TLC and the knowledge of research-orienting laboratory experimental skills. They demonstrate the safety procedures in the laboratory, importance of reproducibility of the results in the laboratory, importance of economical, simple, and time-saving procedure, and at last, understand the advantages of a one-pot catalytic process among the undergraduate students. So these are the most important student learning outcomes that we have reported. So here we share the student post-lab question. This is also available in this particular journal, because according to this journal requirement, we have to send the students' class notes also. So for the post-lab question, we developed the few post-lab questions here. Develop a scheme for bis 4-hydroxycoumarine reaction using 4-nitrobenzaldehyde. Write down the few biologically active bis 4-hydroxycoumarines with structure. Write down the name of few acidic catalysts which used in bis 4-hydroxycoumarine synthesis. Bis 4-hydroxycoumarine synthesis is a multi-component reaction. Explain this. Does any rearrangement occur in this reaction? These are the students' post-lab question. And this is the data, that assessment of student work. That means we observed that from the post-lab question A, 92% student give the correct answer. Answer of post-lab question B, 95% student give the correct answer. Post-lab question C, 90% give the correct answer. Post-lab question D, 84% give the correct answer. And post-lab question E, 73% give the correct answer. So if we consider regarding our pedagogical goal point, that is the obtained desired product, 90% give the correct answer. Yield of the product measurement, 91%. And TLC spot identification, it is also 80%. So assessment of the student work, the pedagogical goals were achieved in the experiment by the laboratory reports. In the lab reports, students reported the product yield, melting point, identified 1H NMR, 13C NMR, IR spectra of unknown bis 4-hydroxycoumarines. Post-lab records have been used for the assessment of the students' performance. And last one, instructor observation for the laboratory skill development, spectral analysis of the unknown compounds, and post-lab questions are also very key assessments of the student work. Now the most important section for the reproducibility of the result. So when you publish anything for the chemical education related journal, and if this journal is SCI related journal, so we can consider that the reproducibility of the student result will be very important, because if anyone follow this undergraduate course, and any other university will want to follow this type of experiment properly, and if they don't repeat this particular result which already reported, this is the drawback of the this is the fault of our discussion. So students gain the particular knowledge that for DHPM synthesis or multi-component condensation reaction synthesis or any other reaction, reproducibility is the predominating factor. And another section, or the important part of the reproducibility of the result is that if the students gain the knowledge about the reproducibility of the result, they can use this idea for their next research work also, if they are perform their work in the R&D or any other section. Now I describe the importance of MCR in organic synthesis. So I just give few examples why MCR is so important for synthesis of the different types of organic molecules also. Here we describe one part that this is our work, that is aldehyde 1,3-diketone and urea combined with each other in a presence of grinding methodology or grindstone methodology at room temperature using a particular catalyst. This is called the L-tyrosine we have synthesized in the laboratory. And this L-tyrosine is a very good neurotransmitter. And we have synthesized this lots of compounds. And after synthesizing these compounds, we get that if we change the different types of aldehydes, we can get the different DHPMs. So if you use the ferrosinyl derivatives, we can change this ferrosinyl derivatives also here. It will be substituted ferrosinyl DHPM compounds.
Professor Anamika, you are not audible. Can you hear me, Professor Anamika? You are not audible right now.
So next I come to the part that DHPM5 carboxymite synthesis. As MCR is an important tool for the organic synthesis, you know this thing that aldehyde and urea, when combined with each other, they develop the DHPM in presence of acetamide, they generate the DHPM5 carboxymides. This DHPM5 carboxymides, synthesis of this particular 5 carboxymides is a not very easy routes are there. So if I use the just one pot technique, it will be much more better option. So this is the beauty of the multi-component condensation reaction. Now let us take the example synthesized DHPM5 carboxymides, what we have synthesized in the laboratory. And these are the synthesized 1H NMR spectra of DHPM5 carboxymides. Right now I discuss the DHPM5 carboxymides with the HRMS spectra because we can know what is the mass of this compound. This is 360.1325. This is given, and the molecular formula it is also given, that is C19H19N3O3Na. So if I want to count the number of carbon, hydrogen, nitrogen, and oxygen, you will get this particular information from this formula. Next, this is another important part of our ferrosinyl substituted 1,4-DHPs. Say, let us take the example ferrocin. When we substituted the ferrocin moiety, we get this compound ferrosinyl substituted hence 1,4-DHPs. So this is the HRMS spectra of the ferrosinyl substituted hence 1,4-DHPs. Right now, I just give the single extracrystalline.
Again, Professor Anamika, you are not audible. Professor Anamika, you are not again audible.
Single extracrystallography of our compound. Next, we discuss about the Nepetine right now. It's a cardiovascular compound. We synthesized it in the laboratory, and this is the single extracrystallography structure of this compound. This is our 2-naphthyl substituted 1,4-DHPs. So we can consider that another important part of the multi-component condensation reaction in unconventional solvent, that is state of art. When you consider the stepwise reaction or single step reaction, we can use in the multi-component condensation reaction an unconventional solvent approach. The conventional multi-step preparation of a complex molecule generally involves a large number of synthetic operations, including extraction and purification processes in each individual step. This leads to not only synthetic inefficiency, but also generates large amounts of waste. And this is dangerous for our environment. So in the multi-component condensation reaction approach, defined as one-pot reaction in which at least 3 different substrates joined through covalent bonds have steadily gained importance in synthetic organic chemistry. So one-pot MCRs often shorten reaction periods, giving higher overall chemical yields than multi-step synthesis, and therefore can reduce the use of energy and manpower. Therefore, the design of new MCRs with green procedure has attracted great attention, especially in the areas of drug discovery, organic synthesis, and material science. Use of unconventional solvent in MCR. We know that recently green chemistry is the pillar of organic synthesis. So volatile organic solvents are the major contributor to the environmental pollution. To remove organic solvents from the chemical process, an important aspect of the green chemistry pertains to elimination of the volatile organic solvents or their replacement by non-flammable, non-volatile, non-toxic, and inexpensive green solvents. Particularly, unconventional solvents also showed a great ability for assisting development of MCRs. So these are the important MCR which has been performed in using the water, which has been performed in the ionic liquid also. So let us take the example. This is the ferrosinyl carboxyldehyde, ammonium acetate, diamidone, and ketone when combined with each other in a single pot in presence of water as solvent. This is an unconventional solvent. We get the compound, one dihydropyridine substituted compound. Another example is that MCR in ionic liquids. This is also the unconventional solvent, and this ionic liquids also very effective to synthesize the DHPMs also. So this is the beauty of the multi-component condensation reaction. And in conclusion, you can consider that MCRs represents the cornerstone of both combinatorial chemistry and diversity-oriented synthesis, and thus have played a central role in the development of modern synthetic methodology for the pharmaceutical and drug discovery research. Second part is that MCR also an important tool in respect of its pedagogical significance, what we have already described, because we can use the MCR experiment for undergraduate level also. And last one, green synthetic protocols can easily be utilized on MCR very easily than linear synthesis. So we can consider that though it is 150 years older reaction, but people understand its utility right now. Okay, thank you everyone. Ma'am, I request you for the poll.
Yeah, what's the second poll? So I'm launching the second poll.
Hi, yes, ma'am.
We'll wait for some time to get the responses, and I will share the result. So I think we have got enough result. I'm closing this poll. Sharing result with all of you. The first, atom economy. The question was, which of the following advantages can be associated to MCR over linear synthesis? The poll result shows that first option, atom economy, that is 25%, less waste generation, that is 21%, less human effort, that is 2%, and all of the above, the fourth choice is 52%. This is the result, Professor Anamika. So you can
correct
tell
answer is last, all of the above.
all of the above, right?
Yes.
Okay.
Yes.
So let's go to the questions. I'm hiding this portion.
Yes.
Now I'll be discussing. I think only one question I have seen. This question has been raised by Dr. Shomi Gangopadhyay. The
Yes.
question is, why nifedipine cause rebound hypertension?
Why?
Why nifedipine cause rebound
Hello.
hypertension? Can you hear me? Can you hear me?
Yes. Ma'am,
Why
please come.
nifedipine cause rebound hypertension? Why nifedipine, that medicine, that high blood pressure medicine that you have discussed, why it cause rebound hypertension?
Actually, it is
Raised by Dr. Shomikan. Yes.
okay. Yes, it's hypertension effect we observed because this is the biological study. Actually, we are doing the organic synthesis, but most of the cases we observed that nifedipine, which contains the NH part, this is the actually NH moiety. It is the 1,4-dihydropyridine moiety which is present. It is most of the 1,4-dihydropyridine moiety. It is observed that they are used as a calcium hypertension agent. This is their structure, and they, when combined with each other in our body, this body part interaction, they give this type of result.
Okay. Next question has been raised by Professor Pratap Mukherjee. His question is, what is the drawback of MCR?
What is the
drawback of MCR?
I can't get it, ma'am. Please kindly.
What is the drawback of MCR?
Oh, very good. What is the drawback of MCR? MCR has definitely certain drawbacks are there. So if I consider that one part, just important that for the natural product synthesis, we have to use lots of stepwise manner. But we tell that we can easily use the one-step reaction and we can easily synthesize this compound. But for natural product synthesis, MCR is still now untouched. This is the drawback of MCR.
Okay, no more questions are there, Professor Anamika. It was a very nice session. It was definitely very informative. Thank you, Professor Anamika Khaskel, for giving such a nice and wonderful presentation. And I thank all the professors, staff members of IEM and UEM faculty members for attending this afternoon session. And thank you all. So let's wind up our session today. Thank you, and stay safe, stay home. Definitely, we will be coming out of this situation very soon. Thanks. Thanks to all IEM and UEM family members. Thank you.
Thank you.